Lesson 7.5, Exponential Functions. Our essential question today is, what do exponential growth and decay graphs look like? We have 5 vocab words. The first one is an exponential function. An exponential function is a nonlinear function of the form y equals ab to the power of x. This may look really familiar to you because we've actually worked with these types of functions before a couple of months ago. It's just that we didn't give them the name exponential functions at that time. We talked about them as nonlinear functions, and we talked about them as geometric patterns, or geometric sequences. So this rule right here looks just like the rule or the formula that you'll see on your formula sheet for geometric sequences, because that was f of x equals ab to the power of x. So the only difference is the y. F of x and y are interchangeable. So now we are going to split our exponential functions into 2 different types, growth and decay. Growth functions occur where a is greater than 0 and b is greater than 1. Decay functions occur where a is greater than 0 and b is between 0 and 1. So that would make b a fraction, like 1/2 or 1/3 or 2/5. So it's a fractional value, where growth is when b is greater than 1, so anything higher than 1, even if it's 1.5 or 1.1. The last 2 vocab words, way back in chapter 1, we talked about the domain and range. At that time, we just looked at XY tables. We looked at values, and we said that all of the x values, would be the domain, and we said all of the range values would be the y values from the ordered pairs. We're going to extend it a little bit more in this chapter, and we're going to look at the domain as all of the possible values for x. So not just a couple of values that are in an XY chart or a table, all of the possible values for x for a function. And then the range, similarly, all of the possible values of y for a given function or graph. This could be a little bit tricky for you, but it's really important concept to learn for advanced math classes. Okay, so for starters, we're going to graph some functions, and we're going to look at a couple that are exponential growth and then a couple that are exponential decay. So this one is pretty basic. I'm going to make a little T-chart table, and I'm just going to put in a couple of numbers to take a look at what kind of shape it's going to have. So I'm going to start with 0. If y is 4 to the 0 power, remember the 0 exponent property said anything to the 0 power equals 1. So 0, 1, it's about there. If I put in 1, 4 to the first power is 4. So it's about here. If I put in 2, this is going to get pretty steep. 16. It's going to be way up here. If I put in 2, that's just an estimate. What about the negative numbers? If I put in a -1, 4 to the negative first power is the same as the reciprocal of 4 to the first. So it will be 1/4. So -1 is going to be about 1/4. If I put in -2, that would be the reciprocal of 4 squared. So that's 1/16. So if I continue my chart, my graph is actually just going to get closer and closer and closer. It's going to get closer and closer to the x-axis. It's never going to actually hit it though. So it kind of looks like it's got a little horizontal piece there from the way I drew it. It really doesn't though. You can tell from these fractions like 1/4, 1/16, the denominator is going to be, you know, the next power of 4, 4 to the third, 4 to the fourth, and so on. It's never going to get to 0 though. Never going to get to 0. So here's what our graph looks like. So this graph, because if you look at it from left to right, it is increasing. Left to right, it's increasing. So this is exponential growth. If you look at our equation over here, y equals 1 times 4 to the x power would be equivalent. So a is greater than 0 and b is greater than 1. So it's exponential growth. Now we need to state the y-intercept, domain, and range. Well, my y-intercept was 1. That's where my graph crosses the y-axis. And then the domain and the range, my values for x, I can put in anything that I want for that domain. Anything. I just chose some numbers that were easy to graph. So my domain is all real numbers. I can put in anything. When you look at the graph, you look at this x-axis, and there aren't any restrictions. There aren't any restrictions at all. That graph is just going to continue on in the x direction. Now in the y direction, for the range, there are no points here in the third or fourth quadrant. There are no points. That graph, my red graph, exponential growth, it never hits the axis. It never hits the x-axis. So x has to be greater than 0. That entire graph is in quadrants 1 and 2. So the values for y have to be positive. We cannot get a negative value. So my intercept is 1, domain, anything, all real numbers, range, x is greater than 0. My next graph, I'm going to make a little chart again on this one. This one's a little bit trickier because if I plug it in, 2 to the 0 power is 1. So then that negative sign out in front turns it into -1 plus 1, which is 0. If I plug in 1, 2 to the first power is 2, so it would be -2 plus 1, so -1. If I plug in 2, -2 to the second power plus 1, 2 to the second power is 4, so -4 plus 1 is -3. So 2, -3. If I plug in 3, -2 to the third power plus 1. 2 to the third is 8, so -8 plus 1 is -7. So about right here. And then if I plug in a negative number, -2 to the -first power plus 1. Remember, 2 to the -first is the reciprocal of 2 to the first. So that would make it 1/2. So -1/2 plus 1, so that's 1/2. So -1 is 1/2. -2. So the reciprocal of 2 squared. So that would make that one 1/4. So 1 minus 1/4 is 3/4. So it's getting a little bit higher. I could keep on doing this. So -2 to the the negative third plus 1. So that would be the reciprocal of 2 to the third. So that would make it 1/8 plus 1. So you can see that it's going to get closer and closer to 1 because these fractions here are basically being subtracted from 1. So you're never actually going to reach 1. So that's important for when we do our domain and range. So here's my curve. So this one from left to right, this one is going downhill. So this is exponential decay. And my intercept, my y-intercept, it goes through 0, 0. So my y-intercept is 0. My domain again is all real numbers. All real numbers. My range on this one, I've got nothing up here, and it never hits 1. So my range is, the y values are all going to be less than 1, less than 1. This next one, we have a fraction. If I start with 0, 1/2 to the 0 power equals 1. Next I put in 1, 1/2 to the first power is 1/2. 1/2 to the second power, 1/2 times 1/2 is 1/4. 1/2 to the third power, 1/2 times 1/2 times 1/2 would be 1/8. And then if I try some negatives, remember that the negative exponent means a reciprocal. So that means that I'm going to flip this over. 2 over 1 is just 2. If I flip this over and change to a positive exponent, I will get 4. 4. So now if I graph this and take a look at it, 0, 1, 1 is 1/2, 2 is 1/4, so these are getting just closer and closer to the axis. And then negative 1 is 2, and negative 2 is 4. So you can see the curve here. Remember, even if my graph looks like it touches the axis, it never does. So this is from left to right going down. So this is exponential decay. Exponential decay. And my intercept, my y-intercept was 1. My domain, again, all real numbers. I can put in anything for x. In my range, there are no points down here below the x-axis. So y has to be greater than 0. Greater than 0. I'm going to skip over this one because we're running out of time here and move on to the next skill. Determine whether the set of data displays exponential behavior and then explain. There are 2 questions that you need to ask yourself in order to figure this out. In red, you see, are the domain values at regular intervals. So we check that first. These are going up by 1 every time, so that would be yes. The domain values are at regular intervals. Then the range values, they have to have a common ratio, So that is a multiplication or division pattern, like when we were learning about geometric sequences. And remember, if it was a division pattern, we did learn how to write that as a ratio that's being multiplied. It just happened to be a fraction. So times 3, times 3, times 3. So I'm going to say yes. So it's multiplied by 3 each time. So for the first one about the domain, that one I said yes. And you could say adding 1 each time, because you're just looking for that to be a common interval. So that's an addition pattern for the domain, but the range has to have a ratio, which means it has to have a multiplication or division pattern. Next one, same thing. So This one is going up 2 each time, so I'm going to say yes, it's going up 2 each time. And then this one, it's going up 5, up 5, up 5, so I'm going to say no, it's not a multiplication or division ratio. So it's not a common ratio. It's not supposed to be an arithmetic sequence, which is what it is. Arithmetic is an adding or subtracting pattern where you've got a common number being added or subtracted each time. So this is not going to be exponential behavior. Okay, this last slide is just kind of a review. Can you identify if these are exponential, if they're linear, or neither? So neither would be anything else. So number 1, that is neither because that's a quadratic. Linear is a line. And exponential, we just saw what those curves look like for exponential growth and decay. So number 1 is a parabola, it is neither. Number 2 is a line, so it's linear. Number 3, that's exponential growth, to be specific. And then looking at the equations, hopefully you remember that this first one would be the same as y equals negative 3x plus 7, so it's linear. Whether it's written in point slope, slope intercept, or standard form, it doesn't matter. As long as you could rewrite it into slope intercept, it is something that's linear. Number 5, exponential and growth again, because it's positive 5. You don't have to specify the growth part. You could just say exponential. And then the last one is going to be neither, because that exponent of 2, 3x squared, if you graphed it, would give you a shape similar to this, quadratic. You should be able to write a summary now, and make sure to check on your teacher's website for your homework problems.